podcast is brought to you by LMU Munich.
Good morning. It's a pleasure to be able to give the opening lecture at this wonderful conference. So the assignment that I was given when I was invited to give this talk was to give an overview of the status of the field. I agreed to do this even though it was obvious to me that I'm incapable of doing justice to all that's happening. So after some agonizing, I've decided to survey some recent developments in a couple of the subjects that are not covered by review talks. But before I do that, I will make a few general remarks. So the first question is, what is the field? Since the discovery of gauge gravity duality and other developments, it's become clear that quantum field theory and string theory, or M theory, are not really distinct subjects. String theory and M theory can be viewed as important components of the logical completion of quantum field theory. So therefore, that makes our field very broad. Furthermore, the boundaries of the field are not sharply defined. As our studies illuminate various aspects of particle physics and cosmology, and our techniques find new applications, more and more topics become appropriate for string theory conferences. So pretty much anything goes. String theory is often viewed by the community as some radical idea for explaining quantum gravity. And, well, as you undoubtedly know, string theory grew out of the S-matrix theory program, which was popular in the 1960s. And for many years, string theory appeared to be a radical alternative to quantum field theory. But in view of the remarks that were on the previous transparency, I think it's clear that string theory and M theory are not radical at all. In fact, they are the most conservative and inevitable ways in which to formulate quantum theories of gravity. And I think this fact deserves to be emphasized when speaking about string theory to non-experts. I don't need to convince the people who are here, but other people may find this surprising. So what is my assessment of the status of the field? Well, I would claim that the field is thriving. It continues. It's not me. Okay. There's some gadget under the podium here. I don't know whose that is. The field is thriving. It continues to attract extremely talented young people, and that's always a very good sign for a field. Impressive progress is being made on many fronts, and there is much enthusiasm. And string theory techniques are stimulating progress in fundamental mathematics and other areas of physics. So before I discuss specific topics in string theory, I would like to share some lessons that I've learned in the course of over 40 years of research in string theory and related subjects. Since someone as old and experienced as I am has been asked to speak, I think I should at least share what I've learned with you. And I wish that these lessons had been emphasized to me when I was a student, because I think it might have made a difference. So lesson number one is, if a theory is meant to solve problem A, but it turns out better suited to solving problem B, might be a good idea to modify your goals accordingly. And an example of this is that the original goal of string theory was a theory of hadrons, but it apparently works better as a theory of quantum gravity and unification. The massless particles should be identified as gauge particles and a graviton, rather than as vector mesons and a pomeron. And it's a curious historical coincidence that Yang and Mills in 1954 originally identified SU2 gauge fields with rho mesons. And so in the early days, string theorists have been doing essentially the same thing. You might say they made the same mistake. A second lesson that I've learned over the years is to take coincidences seriously. One example is that the massless states of the type 2a superstring theory correspond to the lowest modes of 11-dimensional supergravity on a circle. And this fact was known for many years before it was taken seriously. So I can recall in the early and mid-'80s teasing some of my friends who were working on 11-dimensional supergravity, telling them that they were making a 10% error by doing that. But of course, time proved that it wasn't so silly after all. A second example is that it was well known that the conformal group in d dimensions is the same as the anti de Sitter isometry group in d+1 dimensions. And this was known to many people many years before ADS-CFT duality was proposed. So this is another coincidence that, had it been taken seriously, might have led to an earlier discovery. Third lesson is that when working on hard problems, it's often a good idea to explore generalizations which introduce additional parameters that can be varied. The more knobs that you have that you can turn, the better opportunities you have for studying what's going on inside a theory. This lesson seems to be very widely appreciated, and there are many examples in the recent literature. And I'll discuss a couple of these examples in my more specific remarks later, specifically in regard to the omega background for n=2 gauge theories and the ZK orbifold generalization of ADS4 times S7. So I had to decide what specific topics to talk about, and this was difficult since I obviously couldn't talk about all of them. So I first decided I would not say anything about the topics covered by review talks, and there are 7 review talks. This afternoon we will hear from Karch on applications of holographic duality to QCD and condensed matter physics, and tomorrow we'll hear on higher spin holography from Yin and multi-loop methods for gauge and gravity scattering amplitudes by Carrasco. Wednesday, Uranga will talk about string phenomenology. And Thursday, we'll hear about beyond the standard model in light of the LHC by Dinamopoulos, and alternative approaches to quantum gravity will be discussed by Nikolai. And on Friday, Vafa will talk about topological strings and their applications. So I will say nothing about these topics. So I tried to make a list of what are some of the other important topics. And here are some of the other important topics that I won't say any more about other than just to list them. And even this list is certainly incomplete. So a major subject is the integrability of certain large N gauge theories, such as n=4 super Yang-Mills and the ABGM model, and their holographic dual worldsheet theories, which are also integrable, and testing the corresponding dualities. There have been recent discoveries of new holographic dualities. There's a lot of work on dualities that involve Horsova-Lifshitz scaling. There have been interesting developments on C theorems, A theorems, F theorems, and so forth. That covers dimensions 2, 3, and 4. I think there's also been work in higher 5 and 6 dimensions. BPS degeneracies and wall crossing formulas have been a big subject. Microstates and black hole entropy, black holes as fuzzballs, double field theory and U-dual generalizations, attempts to formulate 2,0 superconformal field theories in 6 dimensions, string cosmology. These are all active subjects, and I'll say nothing more about any of them. So I've decided just to make a few remarks about 2 subjects. I don't claim special expertise in either of them, but at least I think I can point to some of the interesting developments that have occurred in the recent years. So these 2 subjects are n=2 gauge theories, and then certain superconformal theories in 3 dimensions with lots of supersymmetry, the BLG and ABJM theories. And I'll organize my remarks by just emphasizing some of the key papers in these 2 topics. And there are many, many others, and I apologize for people who will feel slighted because I didn't mention their contributions. So in n=2 gauge theories, the subject developed very rapidly following the 1994 classic papers by Seiberg and Witten, and further insight was provided by Witten's 1997 geometrical derivation based on a lifting of a type 2A brain configuration to a single M5 brain in M theory. So this is all work from the last century, so it doesn't qualify as recent. So I'll now discuss some of the more recent developments. So anything this century I consider recent. That's a privilege of age. So a first important contribution in this subject was the Seiberg-Witten prepotential from instanton counting by Nikita Nekrasov. And what he did was to introduce a two-parameter generalization of n equal 2 gauge theories, where he had two parameters called epsilon 1 and epsilon 2, and he called this an omega background. So the Seiberg-Witten prepotential became a function of two more parameters, the epsilon parameters, in addition to the Coulomb parameters A and the scale lambda. And the usual prepotential corresponds to epsilon 1 and epsilon 2 going to 0. So what Nekrasov did was to compute the instanton partition function in this omega background, and he found that it determined the instanton contribution to the prepotential as a function of epsilon 1 and epsilon 2, so that the usual prepotential would be attained by sending those parameters to 0. And he used the localization method that he and collaborators had introduced previously for carrying out this calculation. And you can see this partition function wouldn't have existed at epsilon 1 or epsilon 2 equals 0, so it was useful to have these parameters in the problem. Now, skipping ahead 7 years from that work, there was the important work of Gaiotto 3 years ago, where he identified a large class of n equal 2 superconformal field theories as corresponding to wrapped M5 branes on a Riemann surface with punctures that are marked by given in ways that are given by very specific rules that he describes. And the picture that he obtained gave a beautiful generalization of S-duality, where you take the Riemann surface and you can decompose it into pair of pants type diagrams. So you have a pants decomposition of the Riemann surface, and each such decomposition gives a generalized quiver theory, and this set of different quiver theories corresponding to a specific Riemann surface are all dual versions of the same theory, just with different weak coupling limits exposed. He also identified a family of strongly interacting superconformal field theories that provide basic ingredients in this construction. He then teamed up with Maldacena to look at the large n limit of a certain class of these theories to describe the dual M-theory geometry. So using the results that Lin, Lun, and Maldacena had obtained in 2004, they were able to describe the ADS5 times M6 geometry. So specifically, you have to describe the six-dimensional geometry M6. And this geometry involves a function that satisfies a three-dimensional Toda equation, and so they were able to restrict the boundary conditions for that Toda equation that were appropriate for this particular construction. Then there was this remarkable conjecture of Alde, Gaiotto, and Tachikawa a couple of months later, entitled Liouville correlation functions from four-dimensional gauge theories. And what they did was to relate a two-dimensional Liouville theory, or more generally a Toda theory, and that the conformal blocks and correlation functions on the Riemann surface correspond to the Nekrasov partition function of the corresponding four-dimensional n equal 2 gauge theory. And although I haven't written anything about this, I have one speculation on this topic, and that is when you take the AN Toda equation, you consider the large n limit, the two-dimensional Toda system can turn into a three-dimensional Toda system. And I suspect that this three-dimensional Toda system in the M-theory dual corresponds to the large n limit of these two-dimensional Toda theories. So here, this is an example of one of these coincidences which I think ought to be taken seriously. And this also suggests that if you were to just consider finite n, that maybe one of the M-theory 11 dimensions should actually be discrete, as having n points. A couple months after that work, there was the work of Nekrasov and Shatashvili. So the n equal 2 gauge theory, without the omega background deformation, has a moduli space which corresponds to a classical integrable system. And they realized that when you put it in an omega background with one of the epsilon parameters non-zero, that this provides a quantization of the classical integrable system. And the non-zero epsilon parameter, in fact, just corresponds to the Planck's constant of this integrable system. The twisted chiral ring maps to quantum Hamiltonians. Supersymmetric vacuum correspond to beta states of the integrable system. So this was also an interesting observation. A little later, Nekrasov teamed up with Witten, and they wrote a paper, The Omega Deformation, Brains, Integrability, and Liouville Theory. And this reformulates the omega deformation of the four-dimensional gauge theory in a way that's valid away from the fixed points that are used in the definition. And this reformulation allowed them to explain the relation between omega deformation and integrable Hamiltonian systems, as well as the AGT duality that I mentioned earlier. Very recently, I noticed a paper by Hellerman, Orlando, and Reffert entitled The Omega Deformation from String Theory and M Theory. And this paper, and previous ones by the same authors, and possibly other authors as well, gives a string theory construction of omega deformation, where one understands it as what they call a flux trap background, which is T-dual to a flux brane or Melvin background. And they found that lifting to M theory corresponds to wrapping an M5 brane on a Riemann surface with self-dual flux. And if one does what's called a 9/11 flip, which means exchanging which circle in the geometry you view as the M theory circle, allows them to reinterpret this omega deformation in terms of non-commutative geometry. So that sounds to me like an interesting direction to explore as well. So those are my remarks on n=2 gauge theories. And now I'll turn to my second topic, which I'll give a lightning overview of, which has to do with superconformal Chern-Simons theories in 3 dimensions. So the BLG and ABGM theories are theories with lots of supersymmetry, and they have 2 Chern-Simons terms. So the gauge group is a product of 2 gauge groups, and one occurs at level k and the other at level -k. So in the case of the BLG Lagrangian, you have OSP 8/4 superconformal symmetry and an SU2k times SU2 minus k gauge symmetry with 8 real bifundamental matter multiplets. The ABJM theory has OSP 6/4 superconformal symmetry and UN level k times UN level -k gauge symmetry with 4 complex bifundamental matter multiplets. So the BLG theory first appeared in these papers by Bagger, Lambert, and Gustafsson. And I was just looking back into the history of this because I was quite interested in it at the time. And I discovered that there were actually some historical antecedents to it which I hadn't been aware of, even though I perhaps should have been. And that is, there had been previous work on taking n=8 supergravity in 3 dimensions, coupled to n-free supermultiplets, and that's a theory with SO8, n non-compact global symmetry. And it was the possibility of gauging a subgroup of this global symmetry was explored by Nicolai and Samtleben in 2001, and they found that it's possible to gauge SO4 subgroups if you include suitable Chern-Simons terms in the construction. Specifically, they found that you can gauge an SO4 subgroup of the SO8, 4 supergravity theory. And if you do that in a way that leaves the unbroken SO8R symmetry, if you then were to turn off the gravity after you're doing the gauging by sending the Planck mass to infinity, this would leave you precisely with the BLG theory. So, and this fact was pointed out in his 2008 paper by Bergsoft, Ruholm, and Rust. So this BLG theory which was just constructed explicitly using 3 algebras and whatnot, could have been first identified by this route. Now, the BLG theory was constructed in an attempt to find the dual, the conformal field theory dual to ADS4 times S7, and it didn't quite work out for that. The correct solution to that problem was found in the famous paper of Aharoni, Bergman, Jafferis, and Maldacena. And what they did was to generalize the problem. So this illustrates introducing a new parameter, which I was mentioning earlier. And they generalized the problem by considering the orbifold ADS4 times S7 mod of the cyclic group ZK. And they showed that at large n fixed k, the conformal field theory that they constructed is dual to M theory in this orbifold geometry. Furthermore, if you instead do an Atuf type limit where you fix n divided by k and consider the large n limit, that then it's dual to a type 2a superstring theory on ADS4 times CP3. Now this theory is supposed to be applicable for k equal 1 or 2, where the supersymmetry is supposed to be n equal 8, not n equal 6. But their classical Lagrangian only has n equal 6 supersymmetry. So what happens is that quantum effects enhance the conformal symmetry from OSP 6/4 to OSP 8/4 precisely when k is equal to 1 or 2. And I find it very amusing that this is sort of the opposite of an anomaly. We're used to anomalies taking a theory with a classical theory with a certain global symmetry and implying that the quantum theory has less supersymmetry, that quantum corrections break some of the supersymmetry. But here's a case where quantum effects actually enhance the symmetry. So I think that's an interesting fact. You might call it an anti-anomaly. There was work a couple years ago by Kapustin and his students Willett and Yakov on non-perturbative tests of three-dimensional dualities. And this paper tests several conjectured dualities between three-dimensional superconformal field theories using localization methods to compute their exact partition functions as functions of phi Iliopolis and mass parameters. So here again, they found it useful to add parameters to probe the intricacies of the theories. And as this example that they considered was that if you consider the exact partition function of the k equal 1 ABJM theory on S3, they showed that this agrees with that for the n equal 8 super Yang-Mills theory with the corresponding gauge group. And this is a non-perturbative test of the conjectured equivalence in the conformal limit. So this gave very convincing evidence for the enhancement of the supersymmetry as a consequence of the quantum corrections. There was a paper last year by Marino and Putroff entitled ABJM Theory as a Fermi Gas. And building on previous work by themselves and others, this paper derives the end of the 3 has a large n fixed k behavior of the free energy of the ABJM theory. It's been known for a long time from the bulk point of view that the free energy should scale as n to the 3 has, but it had not been shown previously that this in fact is what you get from the point of view of the conformal field theory. And so they used localization to reduce the partition function on S3 to a matrix model, and then in a rather inspired manner, they reformulated it as a partition function of an ideal Fermi gas. And viewed this way, they found it quite easy to carry out the relevant computations and obtain the full series of 1 over n corrections to the end of the 3 has scaling, just from the next to leading semi-classical approximation in this formulation. So they have a calculational framework which essentially corresponds to the strong coupling limit of the type 2a description. So that's the lightning review of the second topic. And so now I think it's time for me to conclude. And so just by way of conclusion, I thought I'd just state some opinions or make some remarks concerning string theory and how it might relate to the real world, which is, after all, the thing that really drives most of us in this business. So as you all know, string theory has many possible vacua. And because of this, there's been a lot of concern that it might not be all that predictive, that perhaps you can come very close to explaining almost any reality by just choosing the right vacuum. And if that were the case, that would be disappointing, in my opinion. But I would say that it's unclear how much of particle physics and cosmology can be described and how much should be regarded as environmental. Some features are undoubtedly environmental. Some people prefer to use the word anthropic, but I like to call it environmental. But this does not mean that they all are. There could be principles that greatly narrow the range of possibilities. So, for example, in the F-theory approach to string phenomenology, people have suggested that contractibility of the 4-cycle wrapped by 7 branes will allow you to decouple the unification scale from the Planck scale, and this may be a desirable thing to do. And such an assumption certainly makes the theory much more predictive than it would otherwise be. So if you're willing to make some educated guesses of that sort, I think many quantities could turn out to be computable. At the same time, I'm concerned that crucial information that's required for correctly extending the standard model to much higher energies might not be experimentally accessible. One fear is that the scale and mechanism of supersymmetry breaking might be examples of things that are not experimentally accessible. Without this information, I think it'll be very difficult to find the correct way to bridge the gap between the TeV scale and the Planck scale. So this is a concern, but despite this concern, I remain very optimistic. The LHC is working magnificently, and experimentalists are doing a great job. They've found the Higgs boson, I think, and I would guess that it's only the first of many experimental discoveries that will take place in this decade. So I'm looking forward to an exciting conference, and I thank you for your attention.
Just to point out that I think the simplest example of anti-anomaly is T-duality itself, because winding is clearly classically quantized, but not momentum.